Welcome back to the Learn WGPU tutorial series. Today we're going over the third tutorial, the pipeline, or more accurately, render pipelines. In this video, we're going to end up with a little brown triangle here. So we're going to basically pass these three vertices, one for each of the points of the triangle, into a render pipeline. We're going to run a vertex shader, we're going to run a fragment shader, and this is what we're going to get on the screen. Now, render pipelines are super interesting for two reasons. One of which is that render pipelines are effectively the same thing as materials, the new high-level material API in Bevy 0.8. And the second reason is that render pipelines encapsulate the programs that we want to write for the GPU. So what this means is that while you write your Rust, and it usually runs on the CPU, when we want to write code on the GPU, we need to write these little shader programs. And the programs that we write in the shader language, WGSL, plus the data dependencies that they have and the outputs and things like that, all combine to make a single render pipeline. The tutorial mentions Vertex, Fragment, and Compute shaders, all three of which are available in Bevy. It also mentions geometry shaders, which I have not seen anybody do with WGPU yet, so I don't even know if WGPU would support geometry shaders. So a vertex shader operates on vertices and any mesh like a cube or a triangle or anything like that. So a vertex is any point. In this case, we're looking at triangles. So the vertices are the points that the lines connect. Triangles, of course, are the way that everything is rendered on a screen. So even if you think you have a square, you probably have two triangles. A vertex shader then operates on these vertice points to do whatever you want it to do. You can move the points around or whatever else. The output of the vertex shader then gets passed into the fragment shader, where the fragment shader handles sort of coloring in all of the rest of the pixels. WGSL, or the Wgpu shading language, is the language that we use to write the shaders. And in the case of WGPU, we use another crate called Naga or Naga. I actually don't know what the pronunciation is there. But we use this Naga crate to take the WGSL that we get in and then output that to multiple different platforms. And this is all done internally inside of WGPU. It's why we're using the WGPU crate in the first place. So if you are running on Windows and you want to target DirectX 12, then you can output code that will run on DirectX 12. So our first step is writing our shaders. In this case, we're going to write a single shader file that will contain the vertex shader as well as the fragment shader. So here we've got a vertex shader in the file shader.wgsl. We've got an output struct defining the types that we're going to output here. So if I remove the sidebar here, you can see that it's a function called vsMain. This choice is arbitrary. The function name choice is arbitrary. In this case, we get a built-in that is the vertex index. We define the vertex index value as the in vertex index variable name, which is going to be a U32. And then we return the vertex output, which in this case is the clip position. And the clip position is a vec4 of an F32. So we just call this the position built in for vertices. And the code here you can see uses var and let. So var is a variable that can be modified. So we define this out variable as being a vertex output. That is our struct up here, which we are going to put a clip position into. If I highlight the clip position variable name, you can see out.clipPosition equals this vec4, which is a vec4 of F32s, where we put in X, Y, 0, and 1. They don't really explain the logic here. So the X position and the Y position, they don't really explain why we're using these numbers, but the I32 is a cast. So in vertex index is a U32. We can cast that to an I32 by using I32. So then we take 1 minus the index and we cast that to an F32, and then we multiply it by 0.5. So the vertex index is presumably going to be something like 1, 2, or 3 or 0, 1, 2. Which means that we're placing different vertices in sort of a horizontal triangle, right? So if we think about this, we can say that maybe the vertex index is 0, right? So 1 minus 0 times 0.5 is 0.5, or 1 minus 1 is 0 times 0.5 is 0, or 1 minus 2 is negative 1, which would be negative 0.5. So we've got a vertice at negative 0.5, 0, and 0.5. And then we do basically the same like kind of little mathy thing to like automatically place the vertices for the Y value. In this case, we're doing this like bitwise comparison with 1. So this is 1U, which is just the number 1. So what we end up getting here is for 0, we get 1. Then for 1, we get 1. So 1 times 2. So 2 minus 1 is 1 times 0.5 is 0.5. So we'll have two indices at 0.5, which are the bottom two vertices of our triangle. And then for 2, we end up with 4 minus 1 is 3 times 5 is like 1.5 or something like that. So we end up with an x value and a y value for all three of the vertices that we're going to generate. And then we return the out to return this from the vertex shader. And then we can put the fragment shader in here as well. So we use this like little decorators for at fragment. And then we define fs main. The fs main name is arbitrary, as we'll see later. We use the output of the vertex shader as the input for the fragment shader. And this will be a common theme. We basically have to output from the vertex shader what we expect to receive from the fragment shader. And then we return a color at location 0 or memory location 0. In this case, it's going to be an RGBA. So it's a vec4 of F32s. So it's a color specified by numbers from 0 to 1. In this case, the fragment shader does basically nothing and just returns a color that is basically brown. So R, G, B, and an alpha value of 1. And that's it. I just realized I forgot to go over let, but let is, in contrast of R, let is sort of like an immutable variable. So X can't be changed and Y can't be changed, but out can have things changed on it. For the location 0 here, we actually do define what that's going to be. So keep that in mind for later. This location 0 is not arbitrary. We are going to define a target later inside of our Rust code that defines what that location means. So they want us to go into our state struct and add a render pipeline, which totally makes sense since we are, creating render pipelines. It gives us two options here for how to sort of bring in the shader that we had. One is much larger than the other. So we can either take the device and create a shader module with the shader module descriptor struct, where we can give it a label of shader or whatever we want to call it. And then we can pass the source in as WGSL and include a string and do some conversion from the string into whatever we need it to be. Or we can do this one, which is the one I'm going to do, which is we let shader equal device create shader module, and we use the include WGSL macro, which I like quite a bit more. So I'm just going to put this somewhere in here after device, and let's pull in and include WGSL from WGPU. So if we look at the top here, we can see WGPU include WGSL, and this is what that looks like and where it is. And we need to create a render pipeline layout. In this case, we use the device again to create the pipeline layout with a pipeline layout descriptor struct. We give it a label, we give it some bind group layouts, and we give it some push constant ranges. The bind group layouts are what define sort of the data that we bind and then update later. So this can be things like textures, for example. And then it has us do some more copy pasting, but doesn't actually finish the code. So I'm going to grab the next piece of code too, I think, and the last one too. I just don't want to be sitting here talking about this code and have a bunch of red lines up. Now I am noticing that we see config here, and I think we define config here. So I'm going to take all this code we just pulled in and put it right below config, but before configure. And you see all these red lines right here? I'm going to bring up the error for that on screen now. So if we look at this compiling Rust program right now, we can see that there is a problem with this. So this is the code as written in the tutorial. It looks like this has been changed to an option wrapping the color target state since this tutorial was updated last. So we're going to wrap the color target state in an option. So that looks like this. We just have a sum wrapping the color target state instead of a none or instead of nothing there. And that gets us back to the expected error, which is missing render pipeline itself because we haven't put it there yet. So this is our render pipeline. We use our device to create a render pipeline. Again, this uses that familiar descriptor pattern of we get a descriptor struct and we pass that to the create function to tell it what kind of pipeline we want it to create. We can label it somehow. In this case, we just label it render pipeline. We get to specify both the entry points for the vertex and the fragment shader. So right here, we have VS main as the function name. And right here for the fragment shader, we have FS main. This is why I said that they were sort of optional, or like not optional, but you can name them whatever you want. That's because we control what functions are going to be called here. The buffers in the vertex shader defines the type of the vertices that we want to pass to the vertex shader. And one thing that I found confusing might not be the right word, but you might be wondering why we're not passing in any vertices here. And it's because our shader is generating those vertices for us from the index. So this is actually, we're generating vertices in our shader, not in our Rust code, which is why this buffers is empty. Technically, we don't have to have a fragment shader. That's why this is wrapped in an optional. And the targets is what we were talking about earlier. So when we do at location 0, right here with a vec4 of an F32, this is the target that we're using. So this is target 0. If you see that we are in an array right here. And this is a color target state target with some format. In this case, it's config.format. I think that's the RG or BGRA unorm if we go look at it. So in this case, it's just whatever format was the supported format for the monitor. The blend mode is replace, which means that we'll be replacing these colors. And I don't think we're masking at all, so that's why we're using color rights all. The primitive field describes how to interpret the vertices when converting them into triangles. I am not sure when this is applied, but you can construct a topology. So a topology in this case is just a shape from a triangle list, which is a list of vertices. And there are a number of different ways to do this. If we look at this example in Bevy, for example, we can see a point list, a line strip, a triangle list, or a triangle strip. So in this case, we're using a triangle list. And the differences between these is basically what the numbers mean when we put them in an order. So for example, a triangle list is a list of triangles. Every 3 vertices comprises a new triangle. So if we do vertices 0, 1, 2, and 3, 4, 5, we'll get 2 triangles because it takes the first 3 and then it takes the second 3 and creates 2 triangles out of them. We, of course, haven't specified any triangle data in our buffers. It is what it is. I would love if there was in this tutorial a little bit more description about how this primitive state triangle list is applied, because we're not actually passing in any vertices here. So I'm not even sure that this primitive state is being used. The front face and the cull mode define what a back-facing face is. So in this case, you can imagine a sphere made up of triangles, right? And each of those triangles has to be defined by a set of 3 points on that sphere. And if those triangles are defined in a counterclockwise way, so all of the triangles are defined in the same way, right? If they're all defined counterclockwise, so bottom left, bottom right, top, something like that, then they're considered forward facing in this case. But as you get to the back of the sphere, the triangles that are defined in the same way as the front reverse. And even though they're defined in the same way, they're facing the other direction. So what we end up with is vertices that will read in the other direction, basically. So in this case, we're deciding that any vertices or any faces that are on the back face of that sphere, so exactly basically half of them, right? If we're looking at a sphere, it's the back half of the sphere, then those are just not going to get thrown into our Vertex shader. So we will never see them in our program because they're getting culled out before we even process. We don't use a depth stencil. I believe a depth stencil is something along the lines of like what you see in Townscaper, where you might have a flat plane on a cube and you want it to look like a window is inset into that geometry, but you don't want to create an actual inset geometry. Like you don't want to create additional vertices. I think that's what the depth stencil is used for. Not sure though. And then we never cover multi-sampling. So shrug. So we've got one sample. We're not masking anything. So everything should be active. And we're not doing any anti-aliasing. So this is also false. Multi-view indicates how many array layers the render attachments can have. Again, array textures are, well, there's an example in the Bevy repo if you want to look into it. So if you go into Bevy examples, shader array texture, then you can find out what an array texture actually looks like in a practical use case. And you can see this reinterpret stacked 2D as array. And all this is doing is basically taking one image. Let's see if I can find it. In Bevy assets, textures, array texture, you can see that there is a square for each texture. So this would be interpreted, for example, as an array texture with 4 layers, a grass layer, a mud layer. Is that water or snow? I can't tell. And then like a sandy layer. But for us, our multi-view is none because we only have one PNG that we're writing to. And then we have to add the render pipeline to our state return type because we want to use it. So if we go down to the render pass, we can see there's a render pass color attachment, which is the equivalent of the location 0 output. Remember, our fragment state targets a color target. So when we look at these color attachments, the first render pass color attachment is going to be the location 0 that is this location 0 color attachment. It's going to be where we're writing this color to. And then we're actually going to be using render pass. So I'll remove the little underscore here and I'll paste these render passes into the same block because I believe they're in the same block. Yeah. Now we are seeing some issues here. So let's find out what those are. Oh, cannot borrow as mutable because it's not declared as mutable. They do add this little mute right here at the top. So it's easy to miss that for sure. So now our program is fine. So we set the pipeline for this render pass and then tell the render pass to draw something with 3 vertices and 1 instance. So these are ranges, which means we're getting a range of 0, 1, 2 here and just the number 0 here. This is where the vertex indices come from in our shader. So before, when we were talking about these vertex indices and this in vertex index, this is literally 0, 1, 2 are the numbers coming in here. So that's why we're getting a triangle. Now I am seeing that this works in WASM right now, which you can see that I'm compiling here. But I'm also noticing that it's pretty flickery in WASM for some reason. So instead of showing you the WASM output, I think I'm going to try to show you the default. Yeah, so here's the native output. And you can see that if we say 0, 0 is in the middle here, then what we end up having is, can I bring this over to the other window maybe? So again, if we look at the shader and we look at the indexes that we now know are coming in, so we get the vertex indices 0, 1, and 2. Like we talked about earlier, we can see x of negative 0.5, x of 0, x of 0.5. So think of the entire window as being from negative 1 to 1. So this point over here would be x of negative 1, 0.5, 0, 0.5, 1. And the same thing vertically. So we end up getting a y index for 0 of 0.5. And then we get negative 0.5, which puts it up. And then we get 0.5 again, which puts it down from 0. So the center of this triangle is 0, 0. And that's it. That's a render pipeline. So a render pipeline, again, is a GPU program, basically. It's the shaders that we write, it's the data that we send, and it's the targets that we are writing to. If you take this over to the Bevy world, then this is a material, basically. There's a little bit of smoothing over I've done there, but it's basically a render pipeline is a material in Bevy. So now we see a brown triangle. And our challenge is to create a second pipeline that uses the triangle's position data to create a color and then sends it to the fragment shader. Then have the app swap between these when you press the spacebar. Hint, you'll need to modify vertex output. So create a second pipeline that uses the triangle's position data to create a color that it then sends to the fragment shader. Okay, I can do this easily. So let's get this committed before we do this. So I'll check out a new branch like I did before, and now we get to work on this. So the challenge is to create a color from the triangle's position data that then gets sent to the fragment shader. So let's do this. I wonder if we can just name this color. So we'll store our color output in location 1. We'll set the color exactly equal to the clip position. So this will give us some colors. Remember, in shaders, vec4s are just kind of like a generic container. So in this case, because we know we have something that is between negative 1 and 1, then we could just reuse that data. And we should be able to do in.color here to return the color for each of the vertices. All right, and here we can see the effect of the shader that we just wrote. So what we've done here is in our vertex output struct, I've defined a location 1 that this color is going to get stored into, and it's going to be a type of vec4 f32. I've chosen location 1 because we already have a location 0, and I don't want to make it look like I'm doing anything with location 0. And then for the out.color, we use this clip position, which is 0 or data from 0 to 1 for each of the positions. And then in the fragment shader, because we're using the same data, basically we're passing data from the vertex shader to the fragment shader, we can return in.color. And that'll give us this vertex coloring, basically. So we end up with a color at this point that is 0, 0, one over here that is 1, 0, I think, 1.5, whatever it is. And then up here we get like a green. So 0, 1. I think these are actually 0.5 now that I think about it. So one thing you'll notice here is that I can change this, or actually I've already changed the code. But if we look at the triangle on the right-hand side here, we have what is basically blown out colors, right? So anything below 0 is going to be 0 here, but we can change that. So instead of having something that is like -5, everything at -5 is blown out. and has to be black, what we can do is we can use a built-in function called smooth step. And smooth step allows us to get a much more appealing triangle here, in my opinion anyway. So smooth step is a built-in WGSL function that allows us to take a lower bound and an upper bound, so basically a range here, and then take a value, in this case X or Y, and pass it into that. And any number that is like negative 0.5 will be 0, and any number that is 0.5 will be 1. So it's allowing us to smooth the range out here a little bit. So then we don't end up getting blown out colors, right? So anything down below 0 isn't going to have to be like super dark or blown out or out of range, basically. We're basically moving the range for that we've calculated for X and Y, which is from negative 0.5 to 0.5. And we're moving that to be from 0 to 1, which gets us this much nicer looking triangle. Now, we already handled handling input in the other video, so I don't know that I'm going to implement the spacebar event. So I think this is basically what I would do if I were going to do that. I would match on this event in the input function. I would check for the keyboard input. I would find the right. So in here, input is keyboard input. And then because this is a keyboard input, we could look for the right scan code for the key that's pressed, and we can get the state. And we could do something with this where we basically did the same thing we did in the last video and set the pipeline or the active pipeline in this event. But we already did that, so I'm not going to go through that whole process. And I'm pretty happy with the triangle that we have here. So I think that's it for today, and we will go over the next tutorial in the next Learn WGPU video. If you have any questions, of course, leave them in the comments. I'm happy to answer anything, and I'll see you later. Have a great day.